Warm greetings. Welcome to the first lecture of the Data Structures and Algorithms series. Here, we will see what DSA actually is first of all. Data structures and algorithms is a fundamental concept in computer science that is used to organize and manipulate data efficiently. What do we mean by this? Well, when a computational problem is thrown at you, the users would be able to approach that with a refined mindset because of two important factors that we will be learning in this course: data structures and algorithms. Data structure is nothing, it is just a way of storing and organizing data so that it can be used efficiently. An algorithm, as you all know, is a finite set of well defined instructions that is used to perform a given task. So our goal here is to minimize the time and space required to perform operations that would be needed in an algorithm. So let us first see what solving problems in computation looks like. It usually involves three steps: identifying suitable data structures, organizing that around the problem, and then applying proper algorithmic techniques. Identifying suitable data structure is what we would be seeing in this particular course. Organizing it is what we would be doing in applying it in codes and actually doing the visual representations. Applying proper algorithmic technique is a separate course all by itself, that which also we would be covering in this channel. So first we'll see what data structures actually are. Like, we keep talking about data structures. What do they actually represent? Well, that brings us to the second concept, abstract data types. An abstract data type is a theoretical model that defines the logical behavior of a data structure without specifying how it is implemented. See, whenever you see the word abstract in computational science, you will have to understand that we are only showing the necessary details to the user. That is, when I talk about, say driving a car, I do not exactly know what happens behind the scenes. Like, I do not have to know how the engine works or how the mechanism of the brakes or anything. All I need to know is that if I press the accelerator, the car would move forward, and if I hit the brakes, the car would stop. Right? That is how abstraction also works in computer science. That is, it defines the operations that can be performed and the rules for performing them. It focuses on what the data type does and not how it does it. That is, we will ignore the behind the scenes working, as I said, and we will only be focusing on what we can gain from it, how we can implement it alone. So these are the characteristics of abstract data types. I would encourage you to remember these 4 points because it is very important even in written exams and everything. Abstract data types help in encapsulation of data. They help in modularity. Modularity is separation of data from implementation. They also help in reusability. Once you define an abstract data type, you can reuse it throughout the session of your code. So that is also a very important feature. The fourth one is naturally abstraction. Users interact only with the operations and are not concerned with the actual implementation, right? So these are the 4 characteristics of abstract data types. Now we have a list of abstract data types here. If if any of this feels unfamiliar to you, do not worry, because we would be covering all of this in great detail in this course only. So yeah, we will just skip through this. We have lists, stacks, queues, decks, sets, trees, and all of this. There are like many more abstract data types as well. But for now, we will stick to all of this. We will see all of this one by one in the upcoming lectures. We'll skip on to the next slide. Now we have the time and space complexities. Well, as I was telling you, we would choose a proper data structure to implement a solution, and we will take 2 important factors into account to see how efficient or how optimal the solution is, and those are time and space complexities. These are very simple terms. Space complexity is the measure of the amount of memory used by an algorithm. Constants and variables, as you can obviously see, use a fixed amount of space, while the input space, that is the space that we call as the variable space, would depend based on the input. Like, a smaller input would require smaller space, an input of say n variables would require a space of n, and so on, right? So that is very simple, that you can see. I've included 2 examples here. A recursive function with a call stack would require big O n of space, and a sorting array in place would require big O 1 of space. So when we see different data structures, we would be studying the space complexities with them alongside. So right now it is enough if you just know the theory, right? So space complexity measures the amount of memory used by the algorithm. It is more than enough if you understand this right now. Next, we will go into the time complexity part. Time complexity measures the amount of time an algorithm takes with respect to the input size. So naturally, this can be divided into two types: static time complexity and dynamic time complexity. Static time complexity depends on the machine itself. It does not depend on your code at all, right? So even if I give a very small code into a very old machine that really requires a lot of time for computation, then the time complexity would naturally be higher. That's what the word static means, right? It is determined even before the code is executed. It is calculated through mathematical analysis, and it is dependent on the computer and then various other features that are not dependent on the code. We are mostly concerned with the dynamic time complexity because this is determined during or after execution of the code. That is, it is based on the runtime behavior of inputs and system state. There are various benchmarks for measuring all of this. We will look into all of that later in the upcoming lectures. Right now, we will look into asymptotic measures. Because as far as asymptotic measures are concerned, it is a very important concept because nobody can actually be sitting down and calculating the time and space complexity for every single algorithm that we create, right? We need something that is more faster and that is more generalized. That is where the asymptotic measures come in. Asymptotic measures describe the growth rate of an algorithm's resource usage, usually time or space, as the input becomes very large, right? So this is for very large inputs. So this is a generalized scheme. Asymptotic measures is a generalized scheme that is used for calculating the time and space complexities of inputs of huge sizes, right? So you need not sit and find out time complexities for every entry one by one. Instead, what you can do is you can know. I'll go to the graph first and then come here. So these represent standard algorithms where the asymptotic measuring of the time and space complexities are already known, and this is the algorithm for which you will have to find the asymptotic measure, right? So once you know the standard, you can gauge how your algorithm would perform, right? Based on this, there are three features: big O, omega, and theta. Big O describes the upper bound. That is, it is the worst case scenario. That is, the algorithm would not take more than this for any number of inputs that you give. This is the worst case performance of the algorithm. That's what big O denotes. Omega is the best case performance of that same algorithm, right? It is the lowest bound. That is, this is the least amount of time an algorithm would take given the best case of inputs, right? That's what omega means. And theta is an average between the two. The algorithm always takes around f of n time in an average case. That's what this means. These are the representations. Big O is represented with a big O naturally. This is how we represent omega, and this is how we represent theta, right? Now we'll look at the graphs once again. This is how we represent the theta notation. That is, if these are the known time complexities, time or space complexities, our algorithm would lie between those two values. That's what this means. This is big O. That is, this is the worst case of the algorithm that the algorithm can perform. This is the worst case performance of the algorithm. And as we saw here, this is the upper bound of performing. That is, it would not take more than this time to run or store the values. And this is the best case of the algorithm. This is the omega value. This is the best case. That is, this is the least amount of time that the algorithm would require in order to run and compute effectively. That's about it. We will see you in the next lecture. Until then, keep learning. Thank you.